Swayam Prabha. Digital India. Educated India.
Hello everyone, this is Dr. Vishal Trivedi from Department of Biosciences and Bioengineering, IIT Guwahati. And what we were discussing about the different properties of the enzyme in the course Enzyme Science and Technology. And so far what we have discussed in the previous module, we have discussed about how you can be able to design the different types of inhibitors. So we have discussed about the traditional approaches, we have discussed about the ligand based approach, receptor based approach, and at the end we have also discussed about the computer based targeted inhibitor design. And if you recall, in the previous module, we have also discussed about the different types, the different types of tools, and as well as we have also discussed in detail about how you can be able to use the docking softwares to design the inhibitors. And in the previous lecture, we have also discussed about how you can be able to study the enzyme inhibitions. So enzyme inhibition can be of two types. It can be of reversible type or the irreversible type. In the irreversible type, the inhibitor is of two categories. One, the irreversible inhibitors, which are actually going to be block the active groups onto the active site. So they will be actually the enzyme active site modifiers, and that's how they will actually going to modify the enzyme in such a way that the enzyme is no longer be active. The other category is the suicidal inhibitions or the mechanism based irreversible inhibitors, where you are actually going to have the inhibitor. When the enzyme is actually going to process the inhibitor, then it is actually going to modify the inhibitor to a more active species or some altered species, and because that altered species will have very high affinity for the active site, it will actually going to block the active site permanently, and as a result it is actually going to cause the suicidal inhibitions, or it will actually enzyme itself is processing the inhibitor and it is converting it into an inactive enzyme. So in today's lecture, we are going to discuss about the other category, which is the irreversible inhibitors. And within the reversible inhibitor, we have the three different types of inhibitors. We have the competitive inhibitors, we have non-competitive inhibitor, and we also have the uncompetitive inhibitors. So let's start the today's lecture. So in the reversible inhibitors, we have the three different types of inhibitors. We have the competitive inhibitors, we have the non-competitive inhibitors, and we have the uncompetitive inhibitors. So let's start discussing first the competitive inhibitors. The competitive inhibitors compete with the substrate for the binding to the active site, but once the bound substrate cannot be transformed by the enzyme into the product. So what the competitive inhibitor is doing, for example, this is the enzyme. Okay, so enzyme is making a interaction with the substrate, right? And that's how the enzyme is getting converted into the enzyme substrate complex, and then this enzyme substrate complex is getting converted into the enzyme plus product, right? So if the enzyme is active, it is actually going to do that. But when you add the inhibitor, for example, you add the inhibitor, right? So when you add the inhibitor will also have the same affinity for the active site as like the substrate, right? So enzyme inhibitor is actually going to compete, and as a result, the inhibitor is actually going to form the enzyme inhibitor complex. And because the enzyme inhibitor complex is no longer be processed, because the enzyme inhibitor cannot be processed, whereas the substrate can be processed to form the product, this reaction will no going to active, right? So this is not going to happen, that the inhibitor is also going to be get converted into some product, right? So this is what exactly going to happen. So you suppose you have an enzyme, right? And suppose this is the active site. Okay, so if this is the active site, it can actually take up the substrate on one side, and it can actually take up the inhibitor on other side. Okay, so if it is taking the inhibitor, right, it is forming the enzyme inhibitor complex. So this is the inhibitor what is going to bind, right? And this is going to be the enzyme inhibitor complex. So this is the enzyme, okay? And when it is interacting with the substrate is also going to do the same, right? It is also going to be binding this, right? So it's also going, this is the enzyme substrate complex, okay? And that's how it is actually going to work. So enzyme is actually going to, so the inhibitor is actually competing with the substrate for the same active site, and that's why this particular type of inhibition is called as the uh, competitive inhibitions. Let's take an example to explain you what is the competitive inhibitor. So the competitive inhibition of the succinic dehydrogenase. Succinic dehydrogenase is an enzyme of the Krebs cycle, right? And what its job is that it is actually going to convert the succinic acid into the fumarate, right? So this is the enzyme, okay, and it has the some of the groups and all that. So this is the three-dimensional structure of the enzyme succinic dehydrogenase, right? And when it is interacting with the substrate, the succinate has the well-defined structure. So because of that, this region, right? You see this region is actually taking up the acid groups, and these groups are also taking the acid group, okay? And then the succinic acid is getting converted into the fumarate, which is actually the product, right, of this reaction, and then the product is going to be released. Now the product in this case is also mimicking the same structure as the succinate. So in this case, what will happen is that if you add the fumarate, for example, then the fumarate is also going to block this active site, and that's how the fumarate can be a competitive inhibitor. Taking this structure into the consideration, the people have developed an inhibitor which is called as the malonate. So malonate is exactly the same structure. You see the same structure, except that you don't have one CH2. Okay, so it only has one CH2. Here you have two CH2. That is the only difference. So what happened is that these groups, this site and this site, these sites are crucial, and this site is where the inhibitor is going to compete. So what will happen is this acid group will go and sit here, right? And this acid group will go and sit here. This is exactly the same as for the succinate. So as a result, what will happen is that it is actually going to form the malonate enzyme complex. And once the malonate enzyme complex is formed, because the succinate can be get converted into the fumarate, but the malonate will not get into the product, and as a result the enzyme is actually going to be get fractionated into the inhibitor complex or the substrate complex. So wherever it is actually going to form the inhibitor complex, that type of enzyme will no longer be active to form the product. So as a result, ultimately all the enzyme is actually going to be get converted into the enzyme inhibitor complex, and this enzyme inhibitor complex is going to be inactive, and that's how the enzyme is actually going to be inactive. Remember that all these interactions are mediated by the reversible forces such as the van der Waals forces, electrostatic interactions, salt bridges and all that, and that's why this kind of inhibition is called as a reversible inhibitions. So reversible inhibition of the enzyme by the competitive inhibitors. So competitive inhibitors compete with the substrate for the binding to the active site, But once they bound, the substrate cannot be transformed into the product by the enzymes. Inhibition by the competitive inhibitor can be reversed by simply increasing the concentration of the substrate. And competitive inhibitor resembles the normal substrate in the 3D structures. And competitive inhibitors are making a complex with the enzyme, and that's how they are forming the enzyme inhibitor complex. So as we remember that when we have discussed about the enzyme, right? So if you have an enzyme which has the active site, this enzyme is actually going to be fractionated into two different types of complexes. One, it is actually going to make a complex with the substrate, right? The other complex, what it is actually going to form is the inhibitor, right? So it's also can make the complex with the inhibitor, right? Now these are actually going to be reversibly controlled. So this is a they are in equilibrium. So this is the enzyme. It is forming a complex with substrate, and it is forming a ES complex or EI complex. And all of these are actually the concentration driven, and that's why it says that inhibition by the competitive inhibitor can be reversed by simply increasing the concentration of the substrate. So for example, when you add the substrate, right, it is forming the ES complex. When you add the inhibitor, it is forming the EI complex. Now, depending upon what will be the concentration of the substrate, the amount of enzyme, for example, if you have 100 molecules of enzyme, you can actually have the 50 molecules here and 50 molecules here. For example, because you have added the 50 molecules of inhibitor and 50 molecules of substrate. Now, imagine a situation that I will add the 80 molecules of inhibitor. Substrate. Okay, so if I add the inhibitor, the 80 molecule, which means I have added another 30 molecules, right? So now what will happen for these 30 molecules, the additional 30 molecules, the substrate concentration will go up, right? So as a result, some of the enzyme which actually going to be free will actually go into this direction. So this means if this will go by increase, there will be a decrease in this particular complex, and that's how it is actually going to be 20. Okay, so there will be only 20 enzyme molecules which will be present in the enzyme inhibitor complex, whereas the 30 molecules, because it can go in the both directions, when there will be a enzyme which is going to be formed, there will be a free enzyme, free substrate which is present, and that's how it is going to be drive in this direction. So if you increase the substrate concentrations, the equilibrium will go into this direction, and as a result you will have more and more enzyme substrate complex. Imagine that if I make it 100, then the another 20 will actually going to be reduced. So the concentration of enzyme inhibitor complex is going to be 0. This means all the enzyme is now present as the enzyme substrate complex, and that's how at this particular stage there will be no inhibition, right? And this is what exactly it is written here, that if you increase the substrate concentration, the substrate is actually going to compete with the inhibitor, and as a result it will be keep removing the inhibitor from the enzyme complexes, and as soon as the enzyme is going to be free, the substrate will go and bind, because it is all driven by the concentration gradient or concentrations. So competitive inhibitor is solely being driven by the concentrations. So if the concentration of the inhibitor will go down, the enzyme will again go back to the free enzyme, and that's how the enzyme is actually going to be active, and it will actually going to catalyze the reactions. So this is what exactly it is saying, that if you have the enzyme, you can actually have the substrate. It's actually going to form the ES complex, and that ES complex is actually going to form the enzyme plus product, right? If you add the inhibitor, right, then it is actually going to form the enzyme inhibitor complex, right? And the interaction or the equilibrium constant for this is actually called as Ki, whereas in this case it is called as the Km. So this means you have an enzyme which is actually going to be under the equilibrium of the substrate, or it is actually the under equilibrium of the inhibitor, right? So if you add the inhibitor, it is actually going to form the enzyme inhibitor complex, and if you add the substrate, it is actually going to form the enzyme substrate complex, which means the for a competitive inhibitor, the enzyme is actually going to be fractionated into the two complexes, enzyme substrate complex or enzyme inhibitor complex. And this means if you have the total enzyme would be the free enzyme, the enzyme substrate complex, and the enzyme inhibitor complex. Okay, so this you have to keep in consideration when we are actually going to discuss about the kinetics. This means and remember that the equilibrium constant for the enzyme inhibition interaction is called as Ki. So the Ki is going to be called as the concentration of the enzyme, concentration of the inhibitor divided by the concentration of the enzyme inhibitor complex. Okay. Now, the velocity of the enzyme interaction is v, right? So you remember that when we were discussing about the Maclaurin-Bentham constant, right? So velocity of this is so this one is called as k1 and this is called as k2, right? So velocity is actually going to be called as the k2 and it is actually going to be breakdown of es, right? This is the direction, right? And when you are going to have the maximum velocity, when you are actually going to have all the complexes as the when you are all enzyme is present as the enzyme substrate complex. This means the Vmax is actually the K2 multiplied by the ET, right? This is the maximum what is possible, right? This means if I divide the V by the total enzyme, right, it is actually going to give me this, right? So K2 ES, right? This is what? This is the equation number 1. This is the equation number 2. And so this is from the equation number 1, you can take this. And the ET, remember this, right? This is the equation, right? So you can put this value here. So you can put that concentration of E plus concentration of ES and the concentration of EI. Okay, so these are the this is the ET, right? So if I put the ET from here, right, I can take this, right? So I can take this V by K2 ET, right? So this is what I can put here, right? And I can be able to do this. So if I take this, I can put instead of this, I can put the Maclaurin-Bentham constant. So you can I put the substrate divided by the Km multiplied by the enzyme E, right? And I can do this whole, right? So I can put the enzyme concentration plus substrate divided by Km bracket, right? And E plus inhibitor divided by Ki, okay, and multiplied by E. Okay, so this I have taken from here. Okay, this I have taken from here, right? And if you solve this, what you are going to get is you are going to get this V is divided by V max equal to S divided by Km and 1 plus, so this I have taken this as the outside, right? So 1 plus S by Km plus I by Ki. Okay, and if you simplify this, what you're going to get is you are going to get this. What you are going to get, you're going to get S divided by Km bracket 1 plus I by Ki plus S. Okay, and this is what is very important equation or very important equation to actually be able to understand the competitive reactions. Okay. Now, if I show you the reactions, so this whole thing I can convert. So this whole thing I can, if I assume this as the alpha, right? If uh, I by ki 1 plus I by ki, if I convert, if I consider this as alpha, then it is actually going to be called as S divided by alpha km plus S. So it can be like this, okay? And this is very important. So V by V max is equal to S by alpha km plus S. So, and alpha is equal to 1 plus I by ki, okay? So let's discuss about how the enzyme kinetics is going to function, okay? So if I plot the substrate concentration, okay, versus the velocity, okay, so in this case, first is we can actually be able to show you the curve, how it actually going to be. So it's going to be like this when you have no inhibitor, okay? So this is the no inhibitor, and you remember that if you take this and put it like this, this is going to be the Vmax, and this is going to be the Vmax by 2, okay? And if I go like this, this is the Km, right? Remember the last time when we were talking about the Maclaurin momentum curve, right? So this is the concentration of the Vmax, Km. Now, when you add the inhibitor, okay, when you add the inhibitor is actually going to take up some of the enzyme, right? So, and that's how it will actually going to reduce the effective concentration of the enzyme. So in that case, it is actually going to take the longer time to reach the Vmax. So that is going to be happen like this, okay? This means it is actually going to take the longer time to reach the Vmax. And as a result, the velocity, the ramping of the velocity is less, right? So this is actually in the presence of the inhibitor. This is in the absence of inhibitor. So when you have the inhibitor, it is actually going to take the longer time, because as you are going to have one concentration of the inhibitor, it is actually reducing the concentration of the enzyme, and as a result, it is actually lowering down the, it is asking the enzyme to go for more time. So, okay, now it will still be able to reach to the Vmax, and as a result the Vmax will remain the same. Vmax by 2 will remain the same, but when you calculate the Km is actually going to be different. So this is actually going to be the revised Km, or I will say the Km when you have the inhibitor. So what you can do, what you can see is this is the Maclaurin momentum curve, right? This is the Maclaurin momentum curve. Okay, if I show you the same thing in the line viewer work plot, okay, so line viewer work plot is also going to give you the better idea about what is exactly happening actually. So this is the Maclaurin momentum curve. So 1 by V divided by 1 by S, right? So first is you have the no inhibition, right? So what will happen is that you have the no inhibition. So this is the curve what you are going to get when you have no inhibitor. So this is the Vmax, and this is going to be the Km. Now when you have the inhibitor, okay, so I'll use the same color, right? So when you have the inhibitor, it is actually going to be, because it is taking longer period of time, so it is actually going to be like this. This means it is going to be this, and Vmax will remain same. So this is going to be in the presence of inhibitor. So what exactly is happening in this? Exactly it's happening is that when you have the competitive inhibition, the Vmax remains unchanged, but the Km is going to be altered. And what will happen to the Km? Km will be on a higher side, which means the enzyme is actually reducing. Enzyme is actually requiring the more amount of substrate to show you the same amount of Vmax. And this is exactly what is going to happen, because the enzyme is now fractionating into this, right? This means effectively the enzyme substrate concentration is getting reduced, because some of the enzyme is getting channelized here, right? So you require more substrate so that enzyme is actually be able to show you the Vmax. And then, so in a competitive inhibition, the Vmax is going to remain unchanged. The Km is actually going to alter. And this is what exactly happened, right? When you have the multiple inhibitors. So when you have the multiple inhibitor and you are going to show like the Lineweaver plot, what will happen is that you are going to have the 1 by S versus 1 by V. So you're going to have the, for example, you are going to have this is going to be no inhibitor, right? And as you will increase the inhibitor, right? So if you increase the inhibitor, it will go like this. It will go like this. So here you are going to have the so for example, alpha is equal to 1 in this case, so there will be no inhibitor. If you alpha is equal to 2, this means you have increased the inhibitor. So this, if you increase the inhibitor, if you're increasing the inhibitor concentration, this means alpha is equal to 4, like that, then you are keep reducing the Km, and this is going to be the minus 1 by alpha Km. Okay, so if the alpha is 1, this is going to be the 1 by Km. If alpha is 2, then this is this, and this and that. And since this is on the minus scale, this is not a problem. Okay, so the slope of this curve is actually going to give you the value of alpha Km divided by Vmax. Okay, so this is the Vmax. This is the 1 by Vmax. Okay, and alpha is going to be 1 plus I by Ki. Okay, remember that. So this is actually going to be very, very useful. So competitive inhibitors are easy to design, because you know the size of the active site, you know the size of the inhibitor, so you are actually going to have the many tools to develop the competitive inhibitors. And there are so many of these competitive inhibitors like 6-mercaptopurine, 5-fluorouracil, azacitidine, cytosine, all that. Okay, and they are actually been having the very, very extensive applications in the field of cancer, virus, and all that. And then these are some additional inhibitors what people have also used. The most popular are the statins and methotrexate and dicoprolol, and all these are actually being used in different types of diseases. So this is all about the competitive inhibitions. Let's more discuss about, so this is all about the competitive inhibitions, and now we'll discuss about the non-competitive inhibitions. So in a non-competitive inhibition, so what are the different properties of the non-competitive inhibitor? So non-competitive inhibition is reversible, but not reversed by the substrate. So that is a characteristic contrasting character. Okay, remember that in the competitive inhibitions, you can be able to reverse the competitive inhibitions by increasing the substrate concentrations. Inhibitor binds at a site other than the substrate binding site. That is another point. It binds reversibly to both free enzyme and as well as the enzyme substrate complex to form the inactive enzyme inhibitor complex or enzyme substrate inhibitor complex. This means the enzyme is going to interact with the inhibitor and it's going to form the enzyme inhibitor complex, or enzyme substrate complex is going to interact with the inhibitor and it's going to form the enzyme inhibitor complex. The inhibitors, how it actually going to function as an inhibitor? So inhibitor actually alter the conformation of the enzyme molecule so that the reversible activation occurs. They are naturally occurring metabolite intermediates. So non-competitive inhibitions, as the name suggests, the enzyme, you are actually going to have the enzyme which is interacting with the substrate, and it is going to form the complex, right? So forward reaction K1, this is K minus 1, and the enzyme substrate complex is going to form, and then it is actually going to form the K2, and it's going to form the product and the free enzyme. Okay. Now, in the non-competitive inhibition, because it is not going to compete, it is actually going to bind a discrete site or allosteric site. So it's actually, because it's binding to the discrete site, it actually can bind to the free enzyme, it actually can bind the enzyme substrate complex. So that's why it actually can bind the enzyme inhibitor, okay, and can form the enzyme inhibitor complex, or it can actually be able to bind here, and it actually can form the this enzyme substrate inhibitor complex. Okay, so this is called as Ki, and this is called as Ki prime. Okay, and once it actually going to form the enzyme inhibitor complex or enzyme substrate inhibitor complex, it is actually going to lead to the no reaction. So remember that whenever the inhibitor binds, whether it binds to the allosteric site or whether it binds to the active site, it will never be processed by the enzyme to form the product. So the Ki, again we will write the reaction for the Ki. So Ki is actually going to be that enzyme inhibitor and enzyme inhibitor complex. Remember that here again the enzyme is now fractionating into the substrate, so it's forming the enzyme substrate complex. Enzyme is fractionating with the inhibitor, so it is forming the enzyme inhibitor complex, and enzyme is also binding to the this, so it's also forming the substrate inhibitor, so it's also forming this. So it's actually getting fractionated into now 3 individual molecular species. And the Ki prime, which is for this, right, is going to be the ES I divided by concentration of ESI. Okay, so we're again going to write V by ET is going to be K2 ES, okay, divided by, remember this is the what is going to happen. So this all are going to be, right, so ET in this case would be E, ES, ESI and EI. Okay, so ET is going to be E plus ES from here, right, then it is going to be EI, and then it is going to be ESI. Okay, so if you solve this, and if you, it is going to be give you this V by V max is equal to substrate. When will be the V max? When will the V is going to be V max? When the E is going to be ET, right? So that is going to be Km bracket 1 plus, sorry, this is right, 1 plus I by Ki plus substrate bracket 1 plus I by Ki prime. Okay, so this is the substrate. Okay, and now if you want, you can actually be able to convert this into another equation, and that would be like substrate divided by alpha Km plus alpha prime concentration of substrate. Okay, so alpha Km, again the same way, the so don't we get confused, right? Alpha is equal to 1 plus I by Ki, and alpha prime is 1 plus I by Ki prime. Okay, so since we don't want to make this so complicated, we have just taken the alpha as the substitute of this. So if this is alpha, this is alpha prime. Okay, so alpha km plus alpha prime substrate concentrations, and so in this Vmax by Vmax is equal to substrate divided by alpha km plus alpha prime s. Okay, and this is very important equation for non-competitive inhibitions. Now we'll see what will be the how the curve look like, right? So curve, if you have the curve, you have a substrate concentration, right? And we'll have the no substrate. So first you are going to have no inhibitor, so it's going to be like this. So it's going to be no inhibitor. Okay, now when you have the non-competitive inhibitor, okay, so when you have the non-competitive inhibitor, it's going to be it's because now there's a difference, right? So sorry, so we'll write all the parameters, right? So this is going to be Vmax, this is going to be, so this is velocity versus this, and this is going to be Vmax by 2. So this is Vmax by 2, and I'll go like this. Then this is going to be the Km. Now we'll show you how the non-competitive inhibitor will look like. Okay, so when you have a non-competitive inhibitor, okay, you are actually trapping the enzyme through an alternate alternate structure. Okay, remember that the inhibitor is actually interacting with the enzyme, and inhibitor is also interacting with the enzyme substrate complex, and as a mechanism it is actually changing or altering the 3D structure of the enzyme. Okay, 3D structure of the enzyme, right? Or I'll say it is actually changing the 3D conformation of the active site. And so as a result, it is actually going to change its affinity for the substrate, or it's actually going to change its interaction with the substrate. So as a result, it is actually going to affect this, and so it will not be able to attain the Vmax. Okay, so in this case the Vmax is going to be like this. Okay, so this is going to be the Vmax when you have the inhibitor. So this is going to be in the case of inhibitor, and you will see this is the, okay, so it's actually going to alter many things. So it's going to alter Vmax, right? So it's going to alter the Vmax. Now we'll show you the Lineweaver plot. Okay, so in the Lineweaver plot, okay, what you're going to do is you're going to plot 1 by S versus 1 by V. Okay, and the slope will be like this, right? So first you are going to have the no inhibition, right? So you're going to have no inhibition. So this is going to be no inhibition. So there will be no inhibitor, right? Now you're going to have the as you will change the as you will actually going to add the inhibitors, it is actually going to affect the Vmax. So it's going to move like this. Okay, so this is actually going to be inhibitor 1, inhibitor 2, so all the concentrations. Okay, so all you see here is, and this is actually the 1 by Vmax. Okay, and this is going to be 1 by Vmax when you have inhibitor. Okay, and this is actually the minus alpha by alpha prime by alpha km. Okay, this means if alpha and alpha primes are not present, then this is going to be minus 1 by km. And you see, as I am increasing the inhibitor concentrations, and it is actually changing the Vmax, so it is also lowering down the Vmax. Okay, so in this case, the non-competitive inhibitions you are actually going to affect Vmax. So the slope of this curve is actually going to give you the information about the alpha Km divided by Vmax. Okay, and remember that alpha is 1 plus uh, inhibitor by Ki. Okay, whereas alpha prime is 1 plus inhibitor divided by Ki prime. Okay, so these are the two things what you have to always remember. Okay, so from the slope you can be able to calculate the Km and Vmax, and this is the Vmax, this is the Km what you're going to get. So the clinical significance of the non-competitive inhibitions. So non-competitive inhibitions are more potent and more problematic than the competitive inhibitors. So there are so many inhibitors what you can use. You can have the inhibitors for the heavy metal toxicity. So for example, the heavy metals. Heavy metals, for example, the metal which contains the silver, arginine, and lead. They are binding with the sulfhydryl groups of the enzyme, and that's how they are actually forming the non-competitive inhibitors. And that's why you remember that all these heavy metals are bad for the human health, because they are actually going to inactivate so many enzymes, and that's how they are actually going to cause the toxicity. Then we have the pepstatin. Pepstatin is a protease inhibitor for the pepsin. Then we have the soybean trypsin inhibitor, which also have the inhibitor for the trypsin. And then we also have the ethanol or the narcotic drugs. So, and that also has the inhibitor for the acid phosphatase. So what happened in the non-competitive inhibition is that it is actually so in an enzyme you have the two different sites. You have the active site, you have the allosteric site. So substrate actually can fit into this active site, right? And so what happen is that inhibitor will go and sit here. Okay, so inhibitor will go and sit in the allosteric site. It does not go and bind in the active site. Okay, so that is the major difference, okay, between from the competitive inhibitions. And once it binds, it actually induces the conformational changes, and because it induces the conformational changes, it's actually affecting the binding of the substrate to the active sites. Either it will reduce the affinity, or it may actually abolishes the substrate binding completely. So either of these cases, the inhibitor is actually going to be very, very potent compared to the competitive inhibitor. So let's see a comparative statement, how the comparison between the competitive and the non-competitive inhibitions. So in a competitive inhibitions, the substrate or the inhibitor both are competitive for the active site. So this is the active site which has all the requisite three-dimensional structures. You have all the interactions, everything available for both inhibitor and another substrate. So whoever will be more in concentration, it will actually go and bind. Whereas in the case of non-competitive inhibitor will go and bind to a distant site. It will always be called as allosteric site, and once it binds, it actually brings the alterations into the active site, and that's how the substrate binding is going to be compromised, or the affinity is going to be reduced. So this is what the tabular form I have given you, a comparison between the competitive and the non-competitive inhibitions. So the competitive inhibition is active in the active site, whereas the non-competitive inhibition may or may not be active at the binding site. Then the structure of the inhibitor, most of the competitive inhibitors are the substrate analogs, but the non-competitive inhibitors are unrelated molecules because they are supposed to bind to the allosteric site. Then inhibitions, in both the cases, it is reversible inhibitions. Then if you add the excess of substrate, the inhibition can be relieved in the case of competitive inhibitor, but it is having no effect onto the non-competitive inhibitor, and that's why the non-competitive inhibitors are more potent compared to the competitive inhibitions. Km, the Km is actually going to be increased in the presence of inhibitors, whereas it is going to be unchanged in the presence of inhibitor. The Vmax is actually going to remain unaltered in the case of non-competitive inhibition, whereas it is actually going to be decreased in the case of non-competitive inhibitor. What is the significance? Significance is that it is actually going to have both of the actually going to have the therapeutic applications, whereas the non-competitive inhibitors are mostly being used in a toxicological applications. So now let's move on to the third category, and the third category is the uncompetitive inhibitions. So uncompetitive inhibitions, the inhibitor is actually going to bind to the ES complex. Okay, so this means it is actually going to affect the Vmax, and Km is actually going to be decreased. Examples are alkaline phosphatase inhibition by the phenylalanine. So in this case, what happened is that the enzyme is actually interacting with the substrate, forming the enzyme substrate complex. Okay, and then this enzyme substrate complex is converting into the enzyme plus product. Now, inhibitor does not have any affinity for the enzyme, but when the substrate binds and forms the enzyme substrate complex, then it actually interacts with the enzyme substrate complex and forms the enzyme substrate inhibitor complex. And this is actually not allowing the any kind of process, so it's going to give you the no product. Okay, so this is exactly what is going to happen. So enzyme, you have an enzyme, it has an active site. Okay, so it's going to interact with the substrate and it's going to form the enzyme substrate, right? It's going to form the enzyme substrate. Now at this stage, if you add the inhibitor molecule will also going to have the additional, so this is going to be substrate, and when you add the inhibitor is actually going to have the additional active site. So on this active site you have the substrate, on this active site you are going to have the inhibitor. So basically when the substrate binds, it actually forms inhibitor binding site. So it actually creates the inhibitor binding site, and that's how the inhibitor is actually going to bind. Uh, this is what exactly going to happen. So the enzyme, which is interacting with the substrate, is giving the enzyme substrate complex. So this is the K1, this is the K minus 1, and then this is actually going to form the K2 is going to form the enzyme plus product, and from here the inhibitor is actually going to form, or the inhibitor is going to interact to give you the enzyme substrate inhibitor complex, right? And this will not going to process. Okay, so this is called as the Ki prime, because remember that we will not going to use we'll use the same convention. So Ki prime also we were using when we were talking about the non-competitive inhibitors. So the Ki is ES I divided by ESI. Okay. Remember that the ET in this case would be E, ES and ESI. Okay, so it's going to be E, ES and ESI. Okay, so these are the three way in which the ET is going to divide. Okay, now V is going to be K2 ES, that is, and Vmax, this is the old thing, actually we are writing the same thing, right? K2 ET, right? When the enzyme substrate concentration is going to be total, right? So V by ET is going to be K2 ES, and instead of K ET you are going to write E ES, sorry, E plus ES plus ESI, right? Now instead of writing the ESI, you can write the KI, ESI and all that, and because of that it is going to be, and instead of E2 ET you can write the K2 ET. then it is going to be S by Km bracket में E, right, and divided by uh, E plus S by Km multiplied by E plus S I, so S I divided by Km Ki multiplied by E. Okay, and if you simplify this, okay, if you simplify this, you're going to get V by V max equal to, because this is the V max, right? So V max, V by V max is equal to S by Km divided by 1 plus S by Km plus Si divided by Km Ki. Okay, and this is what you can use. You can convert this into the, so if you take uh, the average of this, you can actually be able to convert 1 in plus. So see, S is also here, S is also here, so you can take the S out and you can be able to convert this. So ultimately V by V max is going to be S divided by alpha Km plus S. So if you simplify all this, okay, S by Km, S by Km, all this, so you can easily take the S by Km out from here, okay, and then it will actually can be used and cancelled out everything. So then it will actually going to give you, this is the final equation what you are going to get, okay, and this is the equation what you can use to understand all the parameters. Now we'll see the line work plot, how it is actually going to work, right? So you're going to have 1 by S versus 1 by V, okay? And this is what exactly going to happen, okay? So you are going to have the slopes like this, and like this, okay? And this is the no inhibitor, and this is the from here to here. So this is the inhibitor concentration 1, this is the inhibitor concentration no. So increasing inhibitor, okay, and as you increase the inhibitor, what you are going to do is you are, so this is going to be minus alpha by Km, okay. So you'll see that you are actually changing the Km, and you are also changing the 1 by Vmax, okay. So this is the 1 by Vmax, okay. So this is the Vmax when you have the inhibitor concentration 2. This is why it is so, because in this case you are altering the, when the inhibitor binds, it actually induces the conformation, and that's all. So in this case there will be a alteration in the Vmax, so it's going to be altered. Km is also going to be altered, okay, and that is the characteristic of the uncompetitive inhibitors. The slope of this curve is actually going to be Km by Vmax, okay, and the alpha prime in this case would be 1 plus I by Ki prime, okay, and this is what you have to use. So this is all about the mechanism of the inhibition of the enzyme. We have discussed about the reversible enzyme. So we have discussed about the competitive inhibitions. We have discussed about the kinetics of the competitive inhibitions and how it is actually inhibiting the enzyme, and what are what we have learned, that if you increase the substrate concentration, you can be able to relieve the inhibition by the competitive inhibitors. In addition to that, we have also discussed about the non-competitive inhibitors. So non-competitive inhibitors binds to a distant site or the allosteric site, and when they bind to the allosteric site, they are actually inducing the conformational changes, and as a result, it is actually altering the binding of the substrate. Uh, and then we also discuss about the uncompetitive inhibitor. So uncompetitive inhibitor does not have any kind of binding site onto the enzyme structure, but when the substrate binds, it actually creates the binding site for the inhibitor, and that's how it's actually going to bind the enzyme substrate complex rather than the free enzyme. And that's how in either of these cases, it is actually going to affect the KM or the Vmax. So with this, I would like to conclude my lecture here. In our subsequent lecture, we are going to discuss some more aspects of the enzyme in the course Enzyme Science and Technology. Thank you.